Homework 3.4, the rational zero theorem, zeros of polynomial functions, video 3. Homework due Wednesday, May 27th, 2020 at 11:53 p.m. Most teachers would start this lesson with what you see on the board, which we'll go over in a second. If you haven't figured out by now, I'm not like most teachers. I don't like just saying, here's what you need to know, now let's do it. I like to naturally develop the topics that we're doing, even if the use of them seems somewhat artificial, such as, let's find the x-intercepts of this graph. But hopefully you watched the previous two videos, and even if you just kind of followed it, then the following is going to make a little bit more sense than if I just give it to you cold. So to summarize what happened in the last video, let me introduce you to the rational zero theorem. Theorem meaning it has been proven to be true. The proof is a little similar to what we saw in the previous videos, but it's a lot more rigorous. Zero meaning a value that makes a function equal to zero. Rational meaning a ratio of integers, which can include the integers themselves because the bottom of that fraction could be 1. And here's the rational zero theorem. If f of x is a polynomial function with integer coefficients, meaning the numbers in front of the x's can only be positive and negative whole numbers, no fractions, no irrationals, no imaginary numbers, then all rational zeros of f of x, so all integers or whole numbers, or all integers or fractions that make the function equal to 0, all rational zeros of f of x have the following form. They must be a factor of the constant term, the one at the end, over a factor of the leading coefficient, the one at the beginning. You might want to go back to the previous video and watch the conclusion of it, and this will make sense in that context. Again, if f of x is a polynomial function with integer coefficients, then all rational zeros of f of x have the following form. A fraction, the numerator is a factor of the constant term, and the denominator is a factor of the leading coefficient. I forgot to mention that what you're about to see applies directly to homework questions 1 through 4 and is a part of most of the rest of the homework. Don't worry, it's easy to do. For example, let's list all the possible rational zeros of f of x equals 4x to the third power minus 7x to the second power plus 11x minus 6. I'm going to be using the phrase possible rational zeros so often that I'm going to abbreviate it starting now, PRZs. So how do you list all the possible rational zeros according to the rational zero theorem? Well, the rational zero theorem says all of your possible rational zeros, all of your rational zeros have this form. So let's set up every possible fraction of this form. And how do we do that? Well, on the top, you need to write factors of the constant term. What's the constant term in this function? 6. More specifically, negative 6. And in the denominator, we're going to list factors of the leading coefficient. And what is the leading coefficient in this polynomial? Remember, it's the one in front of the highest power, 4. All right, so let's list all the factors. Now, the fact that this is negative 6 and this is positive 4 is actually irrelevant. They can both be positive or both be negative, and this list will be the same, and here's why. Give me a pair of numbers that multiply to give 6. How about 1 and 6? I know it says negative 6. Give me a pair of numbers that multiply to give 6 besides those. 2 and 3. Okay? But what about the negatives? I'll get to that in a second. Give me a pair of numbers that multiply to give 4. 1 and 4. Are there any others? 2 and 2, but we only need to list the 2 once. Now, all of these numbers on top are factors of -6, and these numbers are factors of -4, but each list is only half complete because all of their opposites are also factors. In other words, -1 divides into -6 evenly, as does -6, -2, and -3, whereas on the bottom, -1, -4, and -2 all divide into 4 evenly. So does that mean we have to double the length of the list up here and list all the negatives? You could, but there's an easy way to capture all the possible combinations of pluses and minuses, and that's just to put a gigantic plus minus in front of the whole list. So as we start making these fractions, keep in mind that each one is both positive and negative. All right, so you start by making a list of all the factors of the constant term on the top and all the factors of the leading coefficient on the bottom. Then you begin to create every possible fraction you can. And I'll be honest, it's going to be quite a few in some situations. For example, pick any numerator, pick any denominator, and make a fraction. But the problem is you have to get all of them. So how can we get all of them? Well, we'll use a technique that I teach every time I do this section, where we're going to pick one denominator at a time and then go through all the numerators. For example, let's make every possible fraction over 1. 1 over 1, 6 over 1, 2 over 1, 3 over 1. These are what I refer to as the over 1s, because they're all over 1. And each one is plus minus. You may be thinking, why did I have to write it over 1? Isn't each one equal to the top? 1, 6, 2, and 3. You're correct, and we'll simplify them in a minute. But we got to build them all first, and then we'll clean them up. So those were all my over 1s. So next are my over 4s. And by the way, you can write these numbers in any order you want. If you click view an example, it will probably list them in increasing order. But let's go ahead and do the over 4s. So the over 4s would be plus or minus 1 over 4, plus or minus 6 over 4, plus or minus 2 over 4, and plus or minus 3 over 4. And yes, several of these will reduce. But here's my over 4s, and obviously I didn't space this out well because I still have to do my over 2s. So I'm going to have to insert a line break as I write 2 over 4s. But in order to write my over 2s, I'm going to have to go to the next line. I hate doing that, but we'll just continue down here with the over 2s. So let's make every possible fraction over 2. So plus or minus 1 over 2, plus or minus 6 over 2, plus or minus 2 over 2, and plus or minus 3 over 2. Good grief, how many fractions do we have listed? I know it looks like 12, but there's actually 24, because there's 12 positives and 12 negatives. But once you create this list, then you just clean it up. 2 comments about cleaning up. Number 1, if it's over 1, don't actually write it over 1. So plus or minus 1, plus or minus 6, plus or minus 2, plus or minus 3. Rule number 2, if you run across a fraction that reduces, don't even bother, because it's whatever it reduces to is listed elsewhere. So as we go through the rest of them, plus or minus 1 over 4, that won't reduce. But look at plus or minus 6 over 4. I can reduce that by 2 into plus or minus 3 over 2, which is already listed here. So as you're setting these up, keep in mind that anything that reduces you can just omit because it's included somewhere else in the list. So if you're going to write a fraction and you know it reduces, you can actually just not write it. Like this one, plus or minus 2 over 4, that reduces to 1/2. So we don't need to mess with that. We'll write it when we get to it. Plus or minus 3/4 doesn't reduce. And now we're over here. Plus or minus 1/2, there it is. That doesn't reduce. Plus or minus 6 over 2, that reduces. It reduces to 3, which is already in the list. Plus or minus 2 over 2 reduces to 1, which is already in the list. and plus or minus 3 over 2 doesn't reduce. So the final list is actually a lot smaller. 2, 4, 6, 8. It's only 16 numbers, 8 positives and 8 negatives. But manufacturing a list of possible rational zeros is very straightforward. The hardest part is making sure that you have all the factors, but I think the numbers are going to be manageable enough that that won't be an issue. So to review what just happened, if you have a polynomial function, and the question is what are all the possible rational zeros, you simply make a list of all the factors of the constant term over all the factors of the leading coefficient with a plus minus. Then start building every possible fraction. My advice is to focus on one denominator at a time. After you've made the list, all of the over 1s are just whole numbers, integers, and any fraction that reduces you can just toss out because it's going to be listed somewhere else. So it's not really that bad. Now before we wrap up this video, let me explain what this list of numbers is. It's exactly what its name says, possible rational zeros. That means if there is either an integer or a rational number that makes this equal to 0, it must be in this list. So for example, if I asked you, could 5 be a 0 of this? No, it's not in the list. Could 3 be a 0? It could be. But these are only possible rational zeros. Unfortunately, there's no guarantee that any of them work. All this list is are the ones that might work. But at least now, if we have to guess a 0, because remember the whole thing is premised by, I need to do a division problem, give me a box number. Oh, I'm not going to give you one. All right, well, I'll choose from here. At least we don't just have to guess a number at random. We can narrow it down from an infinity number of numbers to choose from to, in this case, 16 numbers, if we were actually looking for a 0. So questions 1 through 4 on the homework just ask you to make this list. And I believe they're multiple choice questions, so you may be able to visually inspect them. Don't worry, we're going to be practicing this a lot in subsequent problems, as this kind of implies.